Hi guys, today we're going to discuss photonics in computing, or more specifically the use of photons in computing instead of electrons, or light instead of electricity, or the combination of photons and electrons in computing, and what it looks like in terms of computers and networks and some different parts inside the computer. We're going to be covering a lot of ground very quickly today, and here's a little overview of what we're going to be talking about. Concerning the speed of things, nothing's faster than light. As of today, no one's cracked the speed of light, and it still remains to be seen if it's even possible. Light travels at about 300 million meters a second, or about 670 million miles an hour, or 7.5 times around the Earth per second. In comparison, electricity travels less than 1% of that speed through wire. Light travels faster because it has no mass. It's massless, it has no weight, and electricity is made of electrons, which have some weight to them and some mass to them. Electricity also fights somewhat when it travels through wire as electrons push their way through the atoms that make up whatever the wire is made of. Replacing electrons with photons in computers, or replacing electricity with light, is what we're talking about today. Essentially, fiber optics are glass tubes in which light travels through. Fiber optic cable is simply a core made of glass or plastic with a highly reflective cladding around it, encased in some kind of cable. Maybe you've seen fiber optic Christmas trees, or you've used an optical audio cable on your home PlayStation or sound system, or perhaps you had one of the color-changing LED lit fiber optic lamps as a toy when you were young. All fiber optics work in basically the same way. Patterns or a bit stream of light pulses are blasted through the core of the cable, and they bounce off the reflective cladding down the cable around corners and come out the other end in the same shape that they went in. And although we didn't start with fiber optics, we recognized the benefits of optical technology a long time ago. Morse code transmitted with lights and semaphores are early examples of how optical communication has been done. While it's not fiber optics, it's a great example of how we use light to speed up transmission of messages. In the late 1700s, a French engineer developed a system of semaphores built high on towers to relay messages to another tower, and this was much faster than hand-carried letters of the time. Later in the 1800s, Alexander Graham Bell, who invented the telephone, also invented the photophone, which modulated light instead of electricity, but its limited practicality ultimately gave way to the invention of the telephone. In modern technology, Corning Glass is the company that really pioneered the optical fiber technology. In the 70s, advancements were made that ultimately led to the first optics in telephone communications throughout Long Beach and Chicago to transmit telephone conversations long distances reliably. This success was what catapulted the fiber optic era into what it's really become today. Currently, we use fiber optics in computing, mostly in getting data from one place to another, or in networking. There's many benefits to using fiber connections instead of copper wire. You can run 10 gig, basically about 40 kilometers with the fiber connection, compared to 100 meters and just about 1 gig with copper without the use of repeaters or signal boosters. Copper wire has a lot less bandwidth than optical wire, and optical is immune to noise and interference from other wires, as well as almost impossible to tap, very lightweight, and super easy to work with compared to copper. Optical networks are moving towards the desktop, where we're seeing optical connections in that last mile from the server room to your actual computer sitting on your desk, and this is kind of what we see in the next few years that will become more popular. So when we talk about optical processors, we're talking about the use of photons fired from lights or lasers to pass signals through optical fibers into optical transistors, logic gates, ALU, microprocessors, processors, all the way up. And power consumption is generally a lot lower, and reliability over distance greatly improves. In 2010, Intel announced that they'd successfully tested the first silicon-based optical data connections. They measured connection speeds about 50 gigabits per second, or about the same as a high-definition movie every single second. A company in the UK called Optalysis is doing something a little different that further advances optic computing. They're developing really a solution that uses light passing through layers of liquid crystal grids and apply various voltages to change the optical density of those crystals. Using different wavelengths and voltages, they can encode analog numerical data in the streams of light, forming an interference pattern on the backside of those crystal structures that then they can be turned back into a mathematical equation. These liquid crystal layers can be stacked in parallel, allowing multiple complex computations to happen at once. Then the signal can be recombined and the data passed on to a digital sensor that passes that information onward. Regardless of the size of the calculation, data management issues are void in this model that exist in traditional serial computing. Like I said, power consumption is so much less that it's almost none compared to what we use today. The need for this technology in processors is super apparent in the fact that Moore's law has held fast since about 1965, but it's now failing. Intel delayed smaller die sizes until a couple years from now, and that theoretical doubling of transistors on a die every 2 years just isn't happening anymore. There's a point at which Intel and chip manufacturers have said it costs too much and the gains aren't there to keep making these things smaller and putting more transistors on a die. Optical technologies look to remain true to Moore's law by reducing the cost per transistor and therefore allowing more to be placed on a single die without the increased overhead and increased use of electricity that we see with traditional wire transistors. One of the main bottlenecks in computing today is memory, whether it's RAM or your hard drive. We're testing optical memory that uses something called GST, the same stuff that's used in rewritable CDs and DVDs, to basically store data in an optical fashion in a non-volatile memory that we can actually capture data and have it remain there while the power is off. It's still in its developmental stages, but until we can reliably store light with very little overhead in big ways for big data, the potential of optic memory is really yet to be seen. For certain, the future holds unseen advances in fiber optic technology and the use of photonics in modern computer architecture, network connectivity, and the storage of data. We're just getting going in the field of photonics and computing, and most people agree that by 2025, we should see photon-based processors, memory, and last-mile communication networks. For now, we'll have to stick to the transatlantic tunnels and big corporate networks using the technology that we'll soon all know and use to make connections as common as today's USB devices. To think that we're less than a generation away from some really major advances in photonic computing is really amazing. Using light is still something that seems relatively alien to most of us. Much like the day we learned the Earth wasn't flat, we're optimistic, but we haven't quite realized all of the benefits of photons instead of electrons in technology. There's many approaches to harnessing the power of light, and we're hopeful that soon we'll be able to send data whizzing through the world at this speed in everything from processors, personal computers, and last mile networks to big data and private networks that span the globe. Achieve this, and we're one step closer to discovering what, if anything, really exists beyond the speed of light. Thanks for staying with me the whole time, and I hope you enjoyed. Have a great day.